Last time we saw the Stein-Spring dilation theorem in various forms. One way to say it is that every completely positive map can be given in a Krauss representation, and there was this form with the Stein-Spring isometry, and finally one form where you realize a general channel by first coupling to a secondary system, to an auxiliary system, doing a unitary rotation on the whole thing, and then tracing out part of the system. So these are all basically equivalent statements about what we want to call a quantum channel. And so today I would like to talk about, first talk about a very general principle of quantum mechanics, which is very closely related to this to the Stein-Spring form. And this principle is no measurement without disturbance. Okay, in order to talk about these subjects, we need, well, this is a very general statement about measurement processes. So there will be an input system, some quantum system on which we measure something, a Hilbert space H in. And then there will be a measurement result, and also the state after the measurement. I need to say something about the state after the measurement in order to even talk about what I mean by disturbance. So the general picture will be, so this is our operational box. There will be some systems going in, some systems going out, but also there's going to be a measurement outcome. Let's say the name of the whole box is T. And this kind of object, where you could actually say this is a channel whose input is a quantum system, and the output is actually a tensor product of a classical or a combination of a classical and a quantum signal. So there's two outputs, namely the classical measurement result and the quantum system after the measurement. And this general sort of thing is called an instrument. So the terminology goes back to Davies, probably in his book, but maybe earlier. Brian Davies' Quantum Theory, Open Systems. So he coined that term instrument. And let's say this is given by, so it's given by completely positive maps. Now if we're in the Heisenberg picture, it would be Tx from B of H out to B of H in. So this is basically the complete positivity and so on is all the same as for a channel that just turns these input systems to the output systems. Same kind of object. What is different, of course, is now the normalization. We have to distinguish between the different results. And so what should the normalization be? Well, if we don't distinguish what the measurement outcome was, then we just sum over x. And if we're not interested in the state after the measurement, we would trace that out, just forget it, and that would be putting in the identity. So this is the normalization condition. So this would be on the input space, this would be on the output space. Okay, so this is an instrument. And there are two sub-channels here that I can distinguish, each related to, well, basically a marginal of this operation. I could forget the classical part, and I could forget the quantum part. So what do we get? So So this would give, so if you forget the quantum output, what do we get? We get a device, just erase this stuff, right? So this would be behind the curtain. You're not interested in that. You only get an input system. From any input system, you get a measurement result. Right? That's what it is. So of course that's just an observable, and its P of the M elements would be positive operators on H in, and this is the operators that I should choose. So because of this condition, the sum of these operators is going to be the identity. That just means that the whole thing is normalized. Right? Now, if we forget I get, let's say, T, let's just call that thing T. Then I just add up all these operators. I just don't distinguish what the outcome was, and this means that probabilistically I'm just adding up. So this is just a channel. So this is a channel. And this, you could say this describes the overall state change. Well, it's written here in the Heisenberg picture, but of course everything here can also be said equivalently in the Schrödinger picture. And then it's actually the map from input states to output states. And I'm saying overall state change here, not just the state change, because this is the state change that I get if I do not distinguish the output. The measurement output, according to the measurement output. So this is what somebody would see who has access to these output systems, but not to the measurement outcomes. Right? So disturbance here means that there is a non-trivial overall state change. So this box is doing something to my states, right? So it's not the identity. This question of disturbance arises only when H out is equal to H in. Otherwise, there is a dramatic change anyhow, and the question of no disturbance doesn't even arise. But then this would be the identity. So this is the case of an instrument that produces some data. We don't really know which, right? But there is no overall state change, so there is no way of detecting statistically that the system was operating, that this measurement was operating. Disturbance means that this is not the identity. Okay, so we can ask a very general question here, and so question, given T, so I know, let's assume that I know what the overall state change is. Right? So given T, what fx or tx are possible. So, for example, in the situation of quantum cryptography, there are two legitimate users. Let's say there's Alice and Bob, and they send particles down a quantum channel, let's say some fiber, and they can check what the channel does, right? By varying the input and varying the measurement, so they can find out what the channel is. Now, the question they would like to answer is, suppose that this whole line, that somewhere on the way somebody was listening in. This character is typically called Eve the eavesdropper. Right? So what could the eavesdropper have learned? Well, this would be exactly a proper scenario of this type where we have an input, an output. We know what the overall state change is. This is in the hands of Alice and Bob. They can monitor this. They can make statistical measurements to determine what the overall T is. And now they would like to know, what could Eve have learned? Of course, the whole point of cryptography later is to make sure that Eve doesn't learn too much. But then, to answer this sort of question, you have to get this characterization. What could Eve have learned? Right? And so it would be a question of this form. T is given, and I would like to understand what kind of information about the inputs could an eavesdropper have obtained. So answer. Steinspring. The comparison part. So now, well, Steinspring for T, right? So you say that T of A is V star A tensor identity on the dilation space K. So V was a map from H in, H out, tensor K. Now, why is that the right thing to use here? Well, we've looked at the situation where we have two different CP maps, and they are ordered in the CP ordering. Right? So we have the map T, and then we have another map which is also completely positive, but also that the difference is completely positive. Now, this particular map would be one of the TXs. One of the TXs has this property because the sum of all the others is also completely positive. Each one of them is completely positive, so also the sum of all the others. So that is, each of these, for each of these possible x's, there is a unique operator, call it something, let's say, okay. So Tx and A, because Tx is supposed to be completely positive, and T minus Tx is also completely positive, then we know that this is equal to A tensor GXV, and the sum of the GX's is the identity, and these are positive. So this is an observable. Right? So this is what the Steinspring comparison gives us, the comparison part of the Steinspring theorem. So actually, all the possible instruments are compatible with T, are precisely labeled by observables on this dilation space. And that's actually the way to understand the Steinspring dilation. Right? So this is the main interest that we have in the Steinspring dilation, to have this characterization that possible positive decompositions of T into such a sum are actually just given by an observable on the output. You could make a picture out of that. Let me do this here. So this box that we have, So think of it as something, as a device that has a quantum output, namely in K, and measure G here. So what this theorem gives us is, in a way to analyze this box. Right? How could it look like? Well, it could always have this part, which is associated with just the map T, the overall state change. And then there is this space K, and we can interpret everything just as a measurement on K. You could, if you want, you could call this the delayed choice version of this question, where you could actually say, well, Eve could store maybe this system K, and then make a measurement later at her discretion. She could do this decomposition, choose the particular decomposition, that is, choose the particular observable years after the event. Right? So all she would have to do is, in this picture, is to store what came as a K system out of this. Right? So we think of this as a channel, the V as a channel that produces from the input, produces a combined system. And actually this is always an assumption in cryptography. I mean, to actually do this, Eve would need very, very good control of everything. Right? But in principle this would be possible. So this is the most powerful Eve that you can think of. Right? If she could do that, then, well, she certainly can do more than that. Right? So the most powerful Eve would actually get this resolved picture of the channel and maybe store the K system that comes out and make possible measurements later. So again, when we come to discuss cryptography as one of the tasks and resources in the tasks and resources chapter, then we'll actually have to look at this. Right? We have to think of Eve as doing something like this. Okay, so actually, in this picture with of the dilation with a delayed choice, there is another natural restriction appearing, right? So the forgetting, so I'll call this the delayed choice version of the channel of the instrument. So forgetting H out here gives a channel David, what's a good notation for the complementary channel?
Well,
people are using different things, right?
Yeah. My notation is to write a C.
Okay, do that.
I'll do that.
Okay. So there's another channel called a TC. This is called the complementary channel. And it's simply defined by TC. Well, this goes from B of K, this is now the output system, to B of H in. So in the Schrödinger picture, it takes the input system and produces a K-style system out of it. And TC of, I don't know, whatever B is B star of 1 tensor B. So with every channel we can associate this. This is a canonical thing to associate with T because, well, the Steinspring dilation gives you unique objects. But actually, I mean, if you go more into this, we're not going to do that, but if you go more deeply into it, you would allow equivalent, different Steinspring dilation that are in some sense equivalent or stronger than each other. And that gives you a somewhat finer resolution. The complementary channel of the complementary channel, what do you think that is? Well, it's some version of the channel, of the original channel. But reconstructed in this universal Steinspring picture, so it's more like equivalent to the original channel. Okay, so now I still haven't answered my original question, what happens when there is no disturbance? So, corollary. When there is no disturbance, that is, T is now the identity. What can we measure? Okay, so what do we have to do? We have to compute the dilation, the Steinspring dilation of the identity.
You have written when there is
When there is no disturbance. Ah. Thank you. Big difference. Okay, so when there is no disturbance, that just means the state is the same before and after. So what can we measure along with that? And now this is reduced to computing the Steinspring dilation of the identity. Now what's your proposal for that? We'll do the minimal dilation, right? Of course, that is this Steinspring dilation. So we try to make k as small as possible. Now t of x is x, right? So we can write this as the identity on the complex numbers. And, well, I don't know, 100 well, this, anyway, the k is one-dimensional. Right? So you could think of this as v from h in to h out. It's given, so every vector is just mapped, which is equal to h in. Hence c. You could think of this as tensoring with the number 1, which is in this complex one-dimensional Hilbert space. So for tensoring, a one-dimensional space is doing nothing, right? This is kind of the identity of a tensor operation. That is just saying we have a trivial system. But nevertheless, k is one-dimensional. Now, the characterization of the possible measurements that go with this now will be in terms of observables on this space. So they have to be positive 1-by-1 matrices. That is actually they're given by a positive number. Right? So the gx there can only be one thing, which is gx times the identity. And gx is some positive numbers. Gx are positive, and the sum of these guys is 1. Okay, so then let's look at what the tx's are. So tx of whatever, maybe a few x's too many. Let's call this an a or so. Tx of a. Well, then I have to stick in this operator here, but that's just a number. Right? So this comes out, this will be gx, and the rest is still just a. Right? No change will be. Okay, so what is the picture for this kind of device? The picture for that kind of device, again, so we are resolving. So this is h in, h out, which is h equal to h in. And there are some measurement results coming up. This is clearly possible to build such an instrument, but with this form, what it really looks like on the inside is like this. So you just leave the system alone, and then you draw random numbers from some random generator with probabilities gx. Right? So this characterizes a g. Right? But inside, the inner working of such a machine is to just leave the system alone and produce random numbers and sell them as outputs. So another way to say this is that these outcomes here are not correlated with the inputs. You don't see, no matter what you do here, you don't see any difference in these numbers because they are sort of mechanically separated. Right? And so if you don't have any disturbance, then you actually haven't made a measurement. Right? Or your measurement, of course, formally there is such a device, but this, whatever it is, it will not tell you anything about the system that goes through. In that sense, it's not a measurement. Right? So So the conclusion here is no disturbance implies no measurement. So another way to say that, there is no measurement without disturbance. So if a measurement tells you anything at all about the system, there must have been a disturbance. Okay, this is a very important principle, and we are going to, well, this will come up in various places later on. There will be quantitative versions and further things to say about that. But are there questions at this point? Okay, so then I would go on, and so my chapter 1 is still statistical structure. And this was 1.3 something. Yeah, so the 1.4 is going to be entanglement. So we have to, this will be short, relatively short, and just a basic introduction to what we mean by entanglement. And then this will later come up in the resources chapter, where we really look at quantitative measures of entanglement, what you can do with it, and so on. So actually this is the one of the basic operational statements. I think I mentioned that in the introduction even, that Charlie Bennett saying that entanglement used to be a way to subtly humiliate the opponents of quantum mechanics, but now it has become a resource. Right? So, but first of all, I have to tell you what entanglement is. Right? So, so entanglement is a kind of correlation, quantum correlation, quantum systems which does not exist in the classical case. This is not a definition, because there are many, well, kind of correlation is not nothing that is clearly defined, but I'll say exactly what I mean, of course. Right? But this is an overall direction. So correlations between quantum systems this is just given by a state on HA, so HB, right? So the box for that would be a state, and it doesn't really matter which way you draw these arrows, but there are two coming out here, and the idea is that you have a device that produces pairs of systems. So with writing them in opposite directions, I want to emphasize what is sometimes called the separated labs scenario. So we're thinking of two labs which are far away, but they get from each other, but they get a system each from a source. And they are correlated, right? But they really don't talk directly to each other. All they see is these particles coming up. And of course, A and B, if you want, stands for Alice and Bob. And so any state on such a tensor product, Hilbert space, describes some kind of quantum correlation. And how do I get it out? I might make a measurement here, right? So FA, and there would be an outcome, little a, and Bob might also do a measurement, measure an f bar with an outcome b. Fa and Fb would be P over M's. And then the overall probability to C, so the probability to see A and B, given that we've used the devices Fa, Fb, and rho. Right, so this is a probability of A and B, the joint occurrence of A and B, given all the stuff that is written behind the vertical line, is then to be computed according to the rules of quantum mechanics by trace rho Fa Fb. So we discussed that in the context of composite systems in general. So this is the way we actually get correlations. And I think it's time to... So there will be some minutes of erasing. Okay, so these are quantum correlations, nothing to it, right? So it's the same as a probability measure that describes correlations between two classical things. Instead of a probability measure, we now have a state and so on, right? Now, to describe a little bit in what sense entanglement is more than just correlation, I would like to cite Hans Reichenbach, a philosopher of science and of science and of probability, also of quantum mechanics. And he came up with something that he called the principle of common cause. So this means, so whenever, actually I should have looked up his original formulation, but I'll give you my wording here. So whenever you find correlations, seek to explain them. In terms of a common cause. the way this should work is statistically. The observed events should become independent. Should become independent, so uncorrelated, if you wish, conditioned on the cause. So for example, give me an example of a correlation. Birth rates and stork population, or something like that. Both of them increased nicely after the war. And you could conclude from that storks bring the babies. But you could also say that there is a common cause for these two variables that you found to be correlated, namely the general prosperity after the war. That both leads to a greater incidence of storks and also to more babies, right? Something like that. So once you understand what the cause of both of these are, the details of these variables should actually become uncorrelated, statistically independent. Now here, so we have a correlation, and let's say we look at the situation where they're measuring here. No, this was Alice, right? This is Bob. One bad mistake I made once is give a lecture in German and translate Alice and Bob by Anton and Bertha. And I was totally getting confused with a he and she pronouns. So I'll stick to here, no problem, right? So Alice and Bob. Well, we see these correlations and the result. So how could this happen? Well, there could be some kind of common cause box here, called this P, and that actually produces some kind of variable lambda, so maybe 1 to 6, then it would be a dice. And depending on that, you build a new state. Right? So this new preparation depends on lambda, and the same would, this is ball, of course. And right? So I'm saying the correlations in the quantum state might be explained by this kind of classical mechanism. This is certainly a way to produce correlated states. Right? So I choose these guys properly, make some random generator, and then what comes out is not going to be a product state. Right? So certainly, in general, these results will be correlated. They might be completely correlated even. Right? So like 1-to-1 correlation coefficient 1 or so. Right? But this whole thing would then be a model of the box. And but it's very simple to write down what that would be, right, by simply looking at this picture. So there are different cases lambda here, occurring with probability p lambda, and conditioned on this common cause, on the lambda, the state would be rho a lambda tensor rho b lambda. Right? So in other words, your state is a convex combination of product states. And this would be one rendering of Reichenbach's principle of common cause. And states that can be written like this, states like this, are called, well, the dominant modern terminology is separable. My term for it when I came up with the concept was classically correlated. And a general decision of the community is also to call every other state entangled. So So I was thinking about the question, what states you can write in this form in the early 80s, as did Hans Primas, and I wrote a paper in '89, which is now mostly cited for this distinction of entangled and unentangled mixed states. And in that paper, I call these states classically correlated, which I think is a good description. But now, if you look in any book, it will be called separable. Right? So I lost the terminological battle, and it's not the only one that I lost. Right? But separable I think is a very bad term, because you typically apply it in the separated lab scenario. So you have two systems that are separated in every possible way you can think of, except that they share some kind of correlation, but they are separated, right? They're far from each other, they don't interact, and so on. And in that situation, you call these two systems non-separable, which is pretty bad for something that you've just done, right? So this, I think this leads to some confusions, but there's no way to fight such battles, so I'll call them separable as well. Okay, so this defines entanglement. Every state which is not of this form is called entangled. Now let's do some example. Right? So if rho is one of these guys, so it's pure, well, purity just means that there is no proper convex combination. Right? So either there's only one term here, or all these guys are the same. Well, in which case you could just summarize them into one term, right? So there is no convex decomposition. Which means that the rho must be one of these guys. Rho is equal to some rho A tensor rho B. And because this is a pure state, the only way to do this is to have a product vector that defines the pure state. Right? This is very easy to see. So for pure states, the distinction is not so wide. It just means either something is completely uncorrelated, that is a product vector, or you should actually call it entangled. So this is a somewhat simpler distinction, and we actually often find people who confuse that, right? Who explain something about entanglement, but what they're really explaining is correlation. And so there's a distinction here. Entanglement is we use only in those situations where you actually, you cannot describe this on the right graph principle. So probably in most courses you explain entanglement first, and then you explain channels, and then you come to the Choi-Yamarkovsky isomorphism, but we did it the other way around. So under Choi isomorphism, I think Yamarkovsky's name is just too long. Under Choi's isomorphism, what does this become? So it must become a distinction of channels, right? There's a certain kind of channel whose Choi matrix is a separable state. So what are they? Well, how do we make these channels? Now, shall we try with a picture first? So here's the Choi. Well, okay, let me just state the result and then we make the picture. And that's very clear. Okay, so the theorem here is for a channel T from H out to B H in. The following are equivalent. So, of course, I said that we want to characterize those channels whose Choi matrix is separable, right? Choi matrix which is, as it's written as a state, we apply the channel, of course, in the Schrödinger picture to a pure state. I normalize the omega, so it's actually a state. And we apply that to some 1/2 of a pure state, and then this is separable. Now, this is for one particular state, and for this maximally entangled omega state. Oh yes, I should talk about maximum entanglement as well. Okay, so the second is T is entanglement breaking. That is for any state on such a composite system, T star tensor identity. So if I apply the T to just 1/2 of an entangled of any system, right? Then I get a separable state. Clearly, 2 implies 1. Right? And the third condition is a classical, so separability or classical correlation is related to the existence of a classical way of doing things, of producing these correlations. So actually, for the channel, there is a classical operational description, like one way to realize the channel. And T is measure and re-prepare. I'll write it out in formulas, or let's maybe guess. So T of A is, well, the output is generated in the following way. First, I measure an observable, call it the value lambda, so that I get trace rho f lambda. And f is going to be an observable. That's the measure part. Now, these are the probabilities for getting the result lambda. Now, conditional on getting that result, what I re-prepare is some rho lambda. So I have 2 families of objects. One observable f lambda and states that I use for the re-preparation when the result is lambda. Okay. So this matches very nicely. It's a very typical example of the Choi isomorphism. This concept of separability or entanglement for states becomes another kind of classical mechanism for a channel. Of course, I can always do a channel by measuring something and, depending on the result, re-preparing something else. This is clearly gives me, from any input, gives me an output. Perfectly fine, that's the way to write such a channel. And so let's do the trivial directions and leave the rest as an exercise. Yeah?
Well, if I look at those claims that I have a way to prepare things classically, if I look at, for example, BB84 algorithm,
Yes.
and it seems that it can rely only on non-closing theorem, and that there is like no entanglement involved.
There are different ways of analyzing that. Was I saying that entanglement is necessarily involved in BB84? No. No, I didn't say
But
that.
the question is, it seems that this algorithm cannot be classically...
Okay, so actually, for all the standard, for the measure and resend attacks, right? So, okay, so there's one version of cryptography where you have prepare and measure.
Mhm.
So Alice prepares something, Bob measures it, she knows what she prepared, Bob measures something. Then there is, that's one way to do cryptography. The other way to do cryptography is to operate on an entangled state that they share, right? Okay, so this is entanglement based and measure and prepare. And they are sort of related by Choi and also. But it's not, this is not exactly the relation that I'm giving you. Right? So if the channel that in the prepare and measure scheme of cryptography, if that channel is entanglement breaking, its corresponding object would be a separable state, and in either case, you have no cryptography. And so on that level, this matches exactly. So these are the classical objects. They are the boring part, but it's good to understand the boring part well. Yeah.
That's the question. And there are also like some people writing papers about things like called quantum discord and a lot of other different words. And
Oh yeah.
that seems that they do not talk about entanglement, but somehow they say that it's non-classical.
Yes. So just a general comment about that. Of course, we will have to look at the details. There's some good Discord papers, but there's a lot of junk also. Generally speaking, I would say that the question, is something quantum or not, is stupid. It's not. This pretends that quantumness is some sort of like a concept that is defined in natural language, and you just want to make it more precise. But actually, quantumness is all there is in quantum theory. So anything that is described by quantum theory is a quantum thing, right? So you have to be more specific and say what kind of thing you couldn't do in the classical case. Now, I'm describing that one way of representing a state classically that is impossible for entangled states, and that's a well-defined thing. For Discord, you can also give a description like that, right? And for various other things, but this is not quantumness as such. There's no such thing as quantumness. There's separability or classical correlation, and that has a particular technical meaning. But quantumness as such is a very bad concept, because every object is quantum, because quantum mechanics is somehow universal. So what? Right? So quantumness is no concept that is just waiting for a definition, because everything is quantum. But there are certain aspects of quantum theory that you can try to describe more precisely and work out better, right? And that makes sense, but quantumness as such is not a concept worth defining. I know that many papers sound like that, but I don't think it's a good idea to work that way, right? So, and of course, I mean, after how many 90 years of quantum mechanics, we should get used that things are quantum. And announcing that something is not classical is a bit lame. Right? We should be able to say more. Okay, but that's a matter of taste. Okay, let's do the
This in point 3, the channel is given in the Schrödinger form.
Yeah.
Or
What is the A here? It's supposed to be the roll, right? Thanks. Okay, so let's just, I'm not going to give a full proof, which is actually not difficult. You have to just write out the Choi isomorphism and identify the various objects. So I just do the easy part. So if you have a measure and re-prepare channel, this will destroy entanglement. So let us just check that. So if I have I have to look at T star tends to the identity on sigma, right? Sigma is just an arbitrary state. So how would I do this? So it's according, I know what the channel does. So this is a sum on lambda, trace over the first partner, 1 of sigma times f lambda, tensor 1, if you want. So this is a state in state on rho lambda b times p lambda, right? And then you multiply that with rho lambda times 1 if you wish. Right? So if you look at the action of such thing on half a system, then this is basically what it does. This is a partial trace over the first system. Right? So this is a this trace operation is also tensored with the identity, which happens on the other side. Right? So so here's your p lambda. This is the rho. No, I think I had the b downstairs and the lambda on top. Okay. So this is a lambda. And so I'll write it like that. No, rho lambda times the identity, and the partial trace would be sitting here. I think this is kind of confusing with the many additional tensor factors that I put in. So maybe write sigma as a sum of whatever, AI tensor BI. This can always be done if I don't insist on A and B being positive. Right? This can always be done. So we just don't require that they're positive. If they're positive, it would be saying that sigma itself is separable. Right? But then maybe it's better to do the computation like that. Then T star times the identity on sigma would be the sum of lambda. So I do everything on the first part here. So this is a trace of the first factor of AI f lambda tensor so this trace times rho lambda. Right? This is what I do to the first system. And I tensor with BI. I don't do anything on the second factor. So yeah, so you see this the partial trace coming out there. So it's so this the sum lambda, some numbers. There's a sum of a lambda and I. So rho lambda tensor sum I trace AI f lambda times BI. Now you want to see that this is positive, right? And that you have to basically, this is what the partial trace is telling you here. So if you want to compute what that operator is, multiply this with another positive operator, evaluate it, and then you get sigma popping up again, which is a positive operator, and therefore this is positive. So, okay, my original plan was to just write it like that, which I admit is a bit crazy with the partial traces here, and you can get confused, right? But if you want, you can resolve it like that, and this just gives you the entangled form. And 2 to 1 is trivial. And 1 to 3 is looking closely at the Choi isomorphism. Right? Let me just leave it there. Okay, so plan. Okay, so this picture here can be, this is a particular way of representing the observed correlations as by a classical mechanism. There could be more general classical mechanisms. Right? So, so I don't bother to actually write out. So I have this common cause thing in the middle, and instead of I could just measure a classical observability. Oops. So earlier, this kind of box was taking in lambda, preparing the state rho lambda, and then making the corresponding quantum measurement, which gives me the B. So what I looked at before was a way of looking at these elements. So this is a purely classical correlation experiment. So it's now, if you want to get a representation like this, so some map that assigns to every quantum observable a quantum random variable, a quantum measurement. Basically the same thing, right? P of the n in the classical context, it's a partition of unity into positive elements. Huh? And of course also for the B's. And the formula should be that the correlations that we measure at the end is the integral P d lambda, some integral or sum over the weighted sum of the lambdas. Now, there would be the probability to get A given the hidden variable lambda, or the classical variable lambda, and finding for every observable a classical partition of unity, and finding for every, that's the same on the B side, and a probability measure of these parameters lambda, would be building a classical model for the state rho, let's say, and the observables that you've chosen. Right? So this is making classical models. Now, what we've seen is that there are some quantum states for which you cannot make a classical model of this special kind. Because those would just be entangled states. All I've written here is that well, the same correlation, that you get the same correlations, or the state is just a separate one. Right? So there are two different issues here. One is, can you represent a given state as a mixture of product states? That would refer to that kind of classical models where the way you turn the information of the common cause into an output is done in a special way, maybe by preparing another state and then making a measurement on that. Right? This, of course, makes a very clear association between the observable and this response function that appears in the classical model, that has a special form, that has a quantum form. Okay, so some people make the distinction here, for example, Nicolas Giselle, they could talk about entanglement here, and if there's no representation of this form, they talk about non-locality, which is just as bad as non-separability in some ways. But anyway, that's the terminology that some people use. So there are slightly different issues here. Right? One is a direct representation of the state as a mixture of products. The other is the question of the existence of classical models. And these are not the same. These classicality properties of a state are not equivalent. And that's actually the content of that paper from 1989 that I mentioned. So, but one thing is actually clear, that there are some states which cannot have a model of either kind. Right? So, and the way to see that is use the Bell inequalities. Actually, the generalized Bell inequalities precisely describe, oops, showing the wrong background, precisely describe which states can be made modeled like this. Right? Existence of a classical model is the same as is equivalent to all generalized Bell inequalities being satisfied. That's actually the definition of the generalized Bell inequalities. So the fact that we have some quantum states which cannot model in any way as classical states is due to John Bell and these guys. On So beginning with a paper by John Bell from 1964, that paper wasn't quite strong enough to make this conclusion, but a version given by the CHSH guys then allows us to do that. And so I should say a little bit about Bell inequalities. We have like 10 minutes. Who of you have heard about Bell inequalities? This man has, right? You just wrote a thesis about it. So let me see the show of hands again. Can we afford to skip that? A little bit at least, right? So, the basic thing is that classical correlation is satisfied some inequalities. And so the prototype is two parties. And it's involved two measurements. Each and two outcomes. So, how much space do I have? Not much. Huh? So, anyway, if you do these experiments, you have, because you can choose, each party can choose two different measurements. We have 4 different correlation experiments. For those, you have to find response functions if you want to model that. And let me see whether I can write that directly. So the Bell correlation is a quantity that you can measure in the quantum case, but which in the classical case, or in any case, in any of these correlation experiments, so this gives a correlation coefficient, and then the probability, let me write it like that, the probability of getting A and B given Fi for A and Fj for B. So this would be a quantity that depends on I and j. And now I also put a sign in, and let's say these numbers, I and j, I take to be 0 and 1. Right? And so I sum this stuff also over I and j, and put a minus 1 to the power ij. Okay, so this is some number. And the claim is that this number, if there is a classical model, is always less than 2. Now here are just the observed probabilities, right? These are the things that are directly constrained by this equation. These are just these probabilities. So I can compute them classically, I can compute them quantum mechanically. So I can stick in my quantum mechanical probabilities for a particular state and check whether this is true or not. But I can also, and that's of course the first step, I can also put in a classical model and show that for a classical model, this inequality is always true. Right? So, but quantum reaches twice the square root of 2. Right? So this is, and now there are different linear combinations of measured probabilities, different weights in front of this that you can choose. that all give you, well, you can compute what is the maximum in every classical case. Not always easy to compute, but basically you could do that. And then you can compute what is the maximum in the quantum case. And that is very often larger, like in this case. Right? So this is the basic phenomenon. Now, what this tells you is that whatever way your classical your correlations arise, the one that you measure in the quantum lab, they could not be produced by classical numbers. And now I should prove that this is true in the classical case, right? At least. So I guess I can't do this with This is, I left a little bit of the previous blackboard there, right? Had I erased that also, balls would exactly fit. Let's see. So the proof of this inequality is simple. It's even simpler if you allow yourself a little bit more time to generalize it and write some more things. So maybe in this compact form, I was not really helping by making it easier. So the Bell correlation, this is called simply the Bell correlation. In a classical model, is the sum over A and B, I and J, and an integral over the probability. And then I have this factor, AB minus 1. Oh, did I mention that A and B were also to be numbers? This makes sense only if the outcomes are numbers, right? I write them I'm adding them up here, so A, B are plus or minus 1. So AB minus 1 to the ij. Fi of A given lambda Fj. Well, this is one is for Alice, the other is for Bob, but I'll just call them G minimum. Given lambda. Okay. Now, first of all, we have an integral that we can exchange the sum of the integral. And then I want to do the sum on A and B, right? Because I can group the A here together with this factor and the B with that factor. So I introduce an object that I call AI of lambda, which is sum over A Fi of A lambda, right? And the corresponding Bj. And then this expression is rewritten as the sum over A and B goes into these definitions, and I have a sum over I and J minus 1 to the I times J, and the integral is still there. Okay? So the sums over A and B are gone. And I have this expression. So now these numbers, AI, Bj, depending on lambda, of course, they all lie between 1 and minus 1. Why? Because these numbers are between 1 and minus 1, and these guys are probabilities. So of course, if that's everything, if this is only this fi is non-zero only for a equal minus 1, then I get minus 1, and otherwise I get plus 1. So it's somewhere in between. So let me just write this out. Uh-oh. Okay, now the claim is that if the numbers are like that, then these numbers are bounded by 2. And that would conclude the proof, because this is just a probability, so we're averaging over something that is less than 2. Now, how can this number become large? Now, think of this as some number. Now, this goes separately for every lambda. Think of this as some number which is either positive or negative. To make this as large as possible, I choose either this a1 of lambda to be plus 1 or minus 1, so to make this sort of as large as possible. And I do the same here. So a1 and a2, oh, there's a minus here. Right, so the minus 1 to the ij, when ij are 0 and 1, is mostly minus 1 to the 0. Only in the case when they are both 1, I get a minus sign. And I shouldn't have written a1 and a2, but a0 and a1. Okay? Sorry. I've written this so many thousands of times in my life that it's hard to forget the 1 and 2. Okay, so the way to maximize this is clearly to choose the a's plus and minus 1. But by the same token, this whole thing is symmetric in a and b's. I should also choose the b's as 1 or minus 1, right? Which I can, same argument, but after arranging the terms. So the maximum is clearly attained when each one of these numbers is either plus 1 or minus 1. Now, this is an even number multiplied by a sign, still even. Right? This is also an even number. So the whole thing is an even number in this extreme case. There are 4 terms, so it might get 4, but also the maximum might be 2. So now 4 is not reachable because if these two have a different sign, then have the same sign. So in order to contribute 2 to the sum, then this term cancels. So either one of the 2 terms cancels if they're plus and minus 1s. So really only 2 terms are there, each one bounded by 1, therefore the whole thing is bounded by 2. Sorry, we're 3 minutes over time. So tomorrow then, there will be a lecture tomorrow, right? For those who haven't heard. Anybody who wants to hear about the exercises, we are there for everybody to talk to. And there will be a Musterlösung, right? Mm-hmm. So tomorrow's topic will be going on from there a little bit more, and then going to this resources and tasks chapter. Okay, see you then.